Hello, everyone.
And welcome to another episode of Solving Advent of Code in Rust and try to learn Rust in between. I'm Roberto, and we have
Luciano. Hello.
Eugene.
Thank you, everybody, for following along. If you never did Advent of Code is a code challenge that is published every year in the Christmas period. We are working toward the last year one. There are 24 challenges. You can find them on adventofcode.com. We are publishing all our code to a GitHub repository. And we have a YouTube channel where we publish all the recording. You can find the link in the description of the Twitch channel. Last time we did part 10, there was brackets balancing problem, and this time we do part 11, exercise day 11, sorry. So who is going to share the readmes, who is going to share the code, who is going to share everything?
So I'm going to try to share the readme. Let me know if this is readable enough. Probably we can make it a little bit bigger. So first of all, let's try to read this. Remember that this is a game where we are in a submarine. So this year it's all about being underwater and trying to run away while we try to find some sort of a key. So hopefully by the last day of Advent of Code, we will have found the key. But meanwhile, lots of adventures underwater. So today what we have to do, we have to deal with a Dumbo octopus, which, by the way, I want to show you a picture because I remember I saw this. It was pretty cool. So in this kind of animal here, which looks very funny, right?
Make it big. Oh, yeah.
So yeah, you can search it on Google and see a lot of pictures. But basically what happens is that we ended up in a cavern and it's full of these rare bioluminescent Dumbo octopuses. And basically they seem not like the Christmas lights on your submarine, so you turn them off. There are 100 octopuses arranged neatly in a 10 by 10 grid. Each octopus slowly gains energy over time and flashes brightly for a moment when its energy is full. Although your lights are off, maybe you could navigate through the cave without disturbing the octopuses if you could predict when the flash of light will happen. So basically each octopus has an energy level. Your submarine can remotely measure the energy level of each octopus, which is going to be our puzzle input. For example, this is a 10 by 10 grid, and every number is one octopus, and the number represents the energy level octopus. And this is basically what it's saying here. So you can model the energy levels and flashes of lights in steps. During a single step, the following occurs. So the first thing is that the energy level of each octopus is increased by 1. Then any octopus with an energy level greater than 9 flashes. So every step, every output, every octopus increases by 1. And then if the number is higher than 9, there is a flash. The flash, this is the flash, increases the energy level of all the adjacent octopuses by 1, including octopuses that are diagonally adjacent. So basically, if this one was going to flash, it will increase all these ones, these ones, and these 3. They will all increase by 1. And an octopus can only flash at most once per step. So this is also an important thing to keep in mind. Finally, any octopus that flashes during this last step will have its level set to 0.
Okay.
Basically because it uses all the energy.
Does this mean that if, say, a neighboring octopus was at 9, you flashed and you brought it up to 10, does this mean it's going to flash as well? Like, is there a chain reaction on every step?
I think so, and we'll see an example here. So for instance, let's look at this one. Let me make this a little bit bigger for now. So basically we say this is the initial configuration before any step. You can see that all these ones are at 9. So basically the next iteration, they will go at 10 and they will flash. What happens is that they all are 0 because basically they went from 9 to 10, they flash, and therefore they ended up with 0. But also the one in the middle that was 1 is now at 0 because it basically got 1 point of energy from every adjacent one and arrived to 10 as well, flashed as well. And if you look at all the other ones, this one was 9, flashed, so it gave 1 to this one, 1 to this one, and 1 to this one. So this one is now at 3 because increased by 1 by itself, but also received 1 extra point from this one. This one is at 4 because it received 1 point from this one and 1 point from this one plus its own point. So you get the idea, right? We need to implement this mechanism and look at the neighbors, and every flashing one will give 1 point to all the neighbors.
Okay, so chain reactions then are possible.
Yes.
Cool.
So yeah, this is the idea, and then you keep going. And of course, in this step 1, nobody flashed, so everything just increased by 1. If you compare this step. Now here there is a larger example, and yeah, you could make the same assumption that this one flashed, and when it flashes, it should give to the other ones an additional point. And this one flashed as well. So this one was 5. It went to 6 on its own, plus it got 1 point from this one, 1 point from this one, and now it's 8. So I hope that the idea is clear, but if anyone has questions, please ask in the chat. Yeah, here there is a very long example. So the point is, after step 10, there have been a total of 204 flashes, and fast forwarding, it is the same configuration every 10 steps. So this is just another example that skips by 10, and we could be using that for our test. Now, let's see what's the question, at least for part 1. After 100 steps, there have been a total of 1,656 flashes. Given the starting energy levels of the Dumbo octopuses in your cavern simulate 100 steps, how many total flashes are there after 100 steps? And this is our answer.
Okay.
Makes sense?
Sounds reasonable to follow.
How many total flashes are there after 100 steps? Okay.
So, who wants to try to solve this in... Do we do it in Python or in Rust?
If we want to show the Python solution first, then we could move in Rust.
Yeah, it's easier. Let's go with Python first.
Okay.
So let me... Roberto, are you sharing already your screen? I think so. So let me add your screen and attach your screen. And hopefully this is going to work. By the way, we are experimenting with OBS for the first time. So if there is anything weird that you see or hear...
Yeah, like my aspect ratio.
Let me know.
Can I make my window larger?
I think if you... Yeah, I mean, you are sharing... Okay, perfect.
Is this fine?
Yes.
Cool. So this was my input that, again, can be different from yours. Here in this paragraph, I just parsed it to see what we had out of it. So I will keep in memory this as a list of lists. Okay? So all the numbers are in a different cell, and we can address them by Y, that is the row, and column, that is the X. So here is, we parse, we define a step function that takes a grid, increments all the number in the grid by 1.
By the way, I love that first grid thing. That is just one liner with list comprehension, and you totally skipped it. I think it's going to be fun to see how that looks like in Rust by doing all the parse logic and so on, handling errors and so on. So this is, I think, one first thing to compare between Python and Rust, how much more succinct can be Python compared to Rust in some cases.
So I parse the grid, I define my step function, that is keeping an accumulator, is doing the step for all the grid, incrementing it by 1. It say that there are flashes, so just to enter inside the loop. So while there is flashes is false. Then it starts to take all the cell. If the cell is known or is greater than 9, it flash. I increment the counter of the flashes. I set the grid to known because it already flashed, so it can't flash twice in a step. A grid can only flash 1 in a step. Then for all the neighbor, diagonal included, so -1 and all the combination of the possible displacement. If I am inside of the grid, so bound control, I control to be inside the bounds of my grid that I know is 10 by 10. So here I hard coded the size of the grid. Sorry if I was lazy. I will just increment that cell. This except pass is because when I put known in it, if I try to do a +1 on a known in Python, I get an exception, but I'm just fine duck typing. I don't care. When everything is done, if a cell is known, it goes back to 0. Otherwise, it is what it was. And this is basically, you have a grid when you are here with some known where you have the cell that blinked, that flashed, and numbers in the other cells. So now we want to give back the grid with the known replaced by 0 because we start a new, like in the Readme, we have zeros there. And the total counter of how many flashes we add in this step. We do our main part here, so we declare another counter, another total counter. We loop 100 times. The grid is equal to the step on top of the grid. Grid and the counter is equal to the step on the grid. I put the accumulator of the step in the global accumulator, and I return it.
I have a question. When you define a function like your step function and you receive grid, is that a reference or it's a copy of the original grid? Like when you do mutations, are you changing the original grid, or it's you are just
if you do mutation on top of this, you get a reference. The short answer is you get a reference to the list. So if you change this list, you're going to change the list you got. But here I'm shadowing the grid with another variable called the grid. So I'm taking the original grid, that is this one. This list comprehension is making basically a copy of the grid, changing numbers, and putting that in a variable with local scope grid that is basically overriding this one. So after this line, I'm not touching anymore the original grid.
Okay, so you're essentially, it looks like a map, but it's list comprehension as opposed to mapping over a list. You're returning a new list of new values.
Yeah, I'm returning a new list of lists.
Yeah.
Okay, for all the x plus 1, for all the x in y, for all the y in grid. So yeah, instead of x and y, I could have called it column and row, but the concept is the same. One is y, the other one is x.
You took a very functional approach there of receiving an input, not mutating it, returning a change copy of that input.
I like it. I return a new list of lists and a counter of how many flashes I had in this step.
I like it.
So on. And I use the trick of having a known to mark the cell as flashed.
Rather than using 0, I suppose, right? Because
if you use 0, you can go in the scenario that you flash a side of that cell and then you increment 0. And that's because the cell that flashed at this step must come out as 0 in the next step.
Right, yes, fair enough. That's a good one. I think when I implemented this, I fell for this one and I spent a lot of time debugging.
I think the alternative is to have kept a list of coordinates that flashed and check there before you increment. But that sounds much more expensive than just using a none.
Yeah.
Might be worth checking, but...
If we want, when I did this, I did this. That is basically, this is our input, 10 by 10, and the 8th is 10. And here we can see that at every step, there is basically the +1 that is rising the level of the graph. And then every now and then they go back to 0. When they reach 9, they go back to 0, and so on.
Looks like a wave.
This is more than 100 steps because this is for part 2, but we'll see. So scroll. We can see the Rust implementation now, right?
Yeah,
I think so. Yeah.
If you don't have any other question, if there are no questions in the chat,
feel free to drop your.
I don't see question in the chat, so I think we can jump to the Rust one.
You need to make this a little bit bigger, Eugen.
Yep, I will attempt to present Luciano's solution, which I haven't read through, so this will be fun.
Yeah, will be an experiment on how readable is my Rust code.
Exactly. Is it big enough, do you think?
Yes, at least for me. Feel free in the chat to tell us if you want to increase the font.
Well, we'll take a look live as we go. So, first thing I see here is we define the neighbors, which I presume is a way of finding the neighbors as tuples, right? It's like take an x and a y and they'll go x minus 1, y minus 1. This looks like a convenience type method to me, sorry. So this is presumably used to find the neighbors later. Next, we have a struct octogrid, which is a list of lists.
Yeah, this is basically using const generics, which we have seen other times before, but basically that means that you can specify n when you build the grid, and therefore you can statically define at compile time what is going to be the actual size of the grid. But you have the flexibility in one part of the code to create a grid, for instance, 5 by 5, which I think we do in the tests. And then the real code maybe is 10 by 10. And you in the actual execution, you will create a grid with n equal 10.
Okay. I see there's a few things here, but I suppose we should start with the from string, the parsing, because we can compare it to the Python comprehension.
Mm-hmm.
So we are creating a grid of 0 and n, and hang on, for each row in the line, hang on, are we splitting this anywhere? Yeah, we are. Okay.
Mm-hmm.
So for each row in the lines which we enumerate, and then for each character in each column, we are appending into the grid. Okay. 2-digit, okay. So we're limiting this to 9, I presume, not accepting numbers.
2-digit is basically taking a char and trying to convert it to a digit, because it could be any letter as well.
Yeah.
So when we say read it as a digit, which I think is going to give us I8. I'm not sure. No, I think it might be a U8, because of course it doesn't take the sign, it's just one character.
Yeah.
And then we have to do unwrap, because that might fail if it's not a digit. So we are assuming that the input is fine, so we can unwrap.
Okay.
Not the best error handling strategy, but
it's okay for these tests, I would assume. Also, we're casting it as a U8 on the spot.
So after the unwrap is some other kind of type?
Actually, I'm not really sure. Does it tell you?
I can select this, I presume, right? And it should give me U32, yeah.
U32.
It's possibly a standard implementation. So I presume we're doing this to be more efficient with the memory.
Because the type in our grid, every value is a U8. So eventually we need to push a number into the grid that is a U8.
Now, this is what this is doing, right? This is adding the U8 there. Okay, and then we're returning it. So yeah, this takes a little bit more code, although it's a bit more explicit, I suppose, depending on how used you are to Python.
Now, to be fair, I went for a very imperative approach there with the for loop. I think you could use iterators and combinators of the iterators to do all of that like as a sequence of split, map, and then inside the map, maybe you split again and you map again. And all of that in one call, so to speak, is going to create the entire grid. Here, I just pre-allocated an empty grid with all values as 0, because of course you need to give a value to every item in the grid anyway. And then I'm going through the characters and filling back all the actual values from the input.
Fair enough. Now, what did I skip? An implementation called display. Not yet sure where this is used, so let's go through the code first and see what else we have.
I don't think we actually use that one. Maybe we use it in the test, but basically display, if you haven't seen that before, is a trait that you can implement to define when you try to print an object, how the string version, let's say, of that object is going to look like. In fact, we are basically just returning a result, but inside the result we are effectively like writing. You can see a lot of writes to a formatter, which is kind of a way to push data into a string representation.
Makes sense. Okay, I see we're writing every value in a row, and then we're writing with a new line after a row is finished. Okay, fair enough. So this is just for debugging purposes.
Yeah, exactly.
Nice to take a look in case anybody wants to use this or isn't aware of this, like myself. All right, we'll move on to the iterator, which I presume is the more complicated and more interesting bit of this. So what do we have here? It's an iterator for the octogrid, and it returns an option of self. Interesting.
Yeah, this is in a way similar to Roberto's function step. Rather than it being implemented as a standalone function, here it's implemented with the concept of an iterator, because then you get a bunch of additional features from Rust, like, I don't know, you can do for loop, or you can get the end number in the iterations. So I think it's just more idiomatic in Rust to do it with an iterator.
Okay, so we're storing a will flash and flashed. A vector of things that will flash, which is basically the coordinates, I presume, x and y, right? And then a hash set of also the coordinates. Okay, so we can make sure that a thing doesn't flash twice. That's fair enough. Okay, and we're defining them. I'm curious what this with capacity thing does, because it's the first time I see it.
Yeah, this is just a little trick that you can do, because in Rust, I'm not really sure what's the default size, but basically when you create anything it needs to have a predefined size, right? Because it allocates memory for it, either in the stack or in the heap. And in the case of a vector, there will be some default size. Let's say it's 4, just as an example. Then what happens if you push a fifth element? What's going to happen is that it's going to double that 4 and reallocate it somewhere else and copy all the previous values. So, of course, if you know in advance which one is going to be the final size, you avoid unnecessary resizing because you already have the exact size that you are going to need.
Yeah, that's fair enough.
So this is a way to just say start a new vector with a predefined capacity. So it pre-allocates that amount of space for you. And the same we do for an hash set.
Fair enough. Okay, this makes sense. Next, I see we're going through the rows and then through the columns. We're enumerating over them, and we're mutating. So the cell, if a number is smaller than 10, you add 1 to it. If it's at 10, interesting.
Yeah, you set it as flashed.
So you put it, but wait a second. So it will flash if its value is equal. Oh, and if it's equal after. Okay, I get it now. It's not an else if. I was going to point out it might not work, but I get it now. Yeah. Okay, so if it's more than 10, you add 1. If it's at 10, you will add it to the will flash list set. Sorry. So I presume, yeah, next we go through the octopi that need to flash this time, right?
Yeah, so just as a comment, actually, let's answer this question before.
Oh, we got a question, of course.
If I can highlight it. Again, sorry, we are experimenting with new stuff,
so nothing is working.
So
it should come up on the screen now. So you could use vecnew using with capacity. Is it an optimization? So yeah, this is literally an alternative to vecnew, where in vecnew you are basically getting a predefined allocation, right? So there is a standard which I have no idea what it is. You can probably find it in the documentation. And when you use with capacity, you're actually saying, I don't want the default because I know exactly how much space am I going to need in terms of number of items. So please pre-allocate me a capacity of that size when you create the vector.
And here I have another question that probably... Okay, here I have another question, and the question is, what if you go above that limit? It will allocate memory?
Okay. It will again continue to resize and reallocate memory. So it doesn't prevent you from growing. It's just starting from a predefined capacity.
Okay, so it's not going to give a panic or whatever and kill everything. No, it's growing, but you at that point don't have the optimization anymore because...
Yeah, I tried to look it up. I didn't quickly find what the default value is. But if you do a bit of digging, I'm sure you can find it. Cool, yeah, so it's saving you reallocations in the long run, essentially.
Yeah, because remember, the vector is in the heap. When you have to locate memory in the heap, you have to call the operating system, and that is a slow operation.
Yep, right. So with that answered, I suppose we should look at the flashing logic.
Can I make a comment first here?
Please do, yeah.
Actually, let's continue here with the question. So
there's another question.
There's a follow-up. I'm very slow with this one. I'll need to find a better way to display questions. Right. Using the macro vec is fixed instead. Yes, I think that vec is like calling vec new. So I don't think with the macro you can specify a capacity. No, don't worry. Please feel free to keep asking more questions. And by the way, we are also learning Rust. So we have been discovering these things by bothering other people or by looking at documentation or examples. So we are all here to learn, so don't worry, feel free to ask more and more.
Exactly. The more you ask, the more we will have to learn as well, if we don't know. So yeah, please keep at it.
Right. Yeah. So I was about to say that in Roberto's implementation, you were using null, if I remember correctly, to avoid double increase or multiple time increase in one loop.
Yeah.
Here, what I'm doing, because of course you cannot use different types for one cell. In the grid, you are fixed at this point to U8. So I couldn't use null. I could have used something like create some value and manage optional values in the grid, but that would have been more complicated probably. So here what I'm doing is I am pre-allocating that vector of will flash. And then after that, I use that vector to go through them only once, basically.
Yeah, I can see you're popping them as you go through them. Although this is interesting because this means you have to go through them again, right? Unless you're adding them back in.
There was a suggestion, I think, last time when you do this, instead you do while some and you try to pop from.
Oh yes, we could do it that way as well. Yes, I think that will remove this line 65 because we'll be embedded in the while. We can.
Yeah, you don't have the unwrap. You don't have the wrap. You don't use the is empty.
Yep.
And it's more idiomatic.
Let's keep it in mind for after we review all of it, and we can do the change after. And we can even do some benchmarking, see if it's any quicker. Okay,
good memory, Robert. I already forgot about these tricks.
Nice. Okay, so we're removing the octopus that must flash right now from the list of octopi that will flash. And if it inserts it in the flashed list, which means these are the ones that have just done it right now, right? So this will return a Boolean. Okay, it'll return true if it wasn't already in the hash set, or false if it was, right? And you're trying to say, cool. Okay, so if it hasn't flashed already, mark it as flashed, and then we will go through each of the deltas in that neighbors list that we had at the top, and we go through each of them as I sizes. Oh, geez, this is hard to read, man. I'm sorry.
We are creating a new tuple of coordinates starting from row ID and call ID, summing the delta.
Summing them together. Okay.
So remember that neighbors was like a static.
Sorry, I'll show it so everybody can see. It's a list of tuples.
Exactly, and this is static, so this is never going to change. It gets allocated once. Then we only use it as a reference for the deltas. So we are in a given cell, and we applied these neighbors coordinates to that cell to get all the coordinates of the neighbors.
Do you reckon this is nicer? Because in the past, I remember we did a get neighbors function, which would kind of apply this for you, given an X and a Y coordinate.
We could probably do something like that as well, yeah.
I'm thinking whether one of them is neater than the other, and one of them is quicker than the other would also be a question. I presume they'll be
if you don't call a function, it's always faster to not call a function.
Yeah, that's true.
Even though, to be fair, Rust might decide to inline that function for you.
Yeah,
so you don't see any difference.
Yeah, if you compile optimize, it's going to unwrap and unroll. Sorry, I think it's called unroll.
So yeah, and there will potentially not be what you call it.
The reason why you need to use isides there is because you could go negative.
Oh yeah, of course.
And so size is assigned.
Yeah. So there is a little bit of conversion to do there.
Fair, yeah, there is some safety required because of this. Make sure the neighbor is inside of the grid. Yep. 0 to n as I size, we're defining the boundaries, and if the boundaries contain the new row and column, then we'll define it as a U size.
And then we are using it.
And then we're actually checking if it's smaller than 10 and adding 1 to it. And if it's equal to 10, we're pushing it in the will flash list, which is going to keep growing and decreasing as things flash. Okay. Hopefully you could all follow along with that. I'm not super certain if I made a lot of sense. But yeah, essentially you go through the octopi that must flash. You remove one from the list. You push it in a list of octopus that, or try to push it in a list of octopuses that have flashed. If that's possible, it means that it's actually flashing this time. So you need to go find its neighbors, see if they will also flash or if they already flashed, and add them to the will flash list. So you keep flashing everyone who has to flash.
Here there is a little bit of code. Here there is a little bit of code duplication between line 77 and 82 with the other lines in the previous loop.
77
that are very similar.
Oh, you're right. Yeah, because we're re-increasing.
Yeah, it's similar.
The two blocks, those two blocks are very similar. So, but this was just a notice, not a critique.
Yeah, true. It could maybe be abstracted in some way. Okay, what else is there? Next, make sure that all the flashed ones are set to 0. So this is iterating over the ones that flashed.
And resets them.
Resets them to 0. Fair enough. And then it's returning however many have flashed this time. Oh yeah, because we're keeping a reference to the grid and we're mutating it. Okay, fair enough.
Now, one comment there is you might wonder why we use some flashed len. And this is because in the iterator trait, when you create that next function, you basically have to say, is this the last iteration? Like, did we complete iterating? And the way you say that is that if you return some value, it means, no, this is still, we are still in progress and this is the current value. If you return none, that means, okay, there is nothing else to iterate over. So this is why we are wrapping it into a sum, which might look a little bit weird if you don't know the iterator trait. Now,
and we will never return known. What is when you have nothing known?
Yeah.
Because this can continue forever. Like logically, you can continue iterating over this game and simulating the evolution of the octopuses as long as you want.
Yep.
Okay, there is a question, I believe.
Okay.
I did not understand how you manage the border of the grid. Is there a specific check? That's a very good question.
Yeah, we can look at it here. So we're defining the boundaries between 0 and n, which is basically however many rows however many columns we have, right?
And rows as well, so you can think about that because it's a square.
Yeah. And then it checks if the new ID, which is the one created based on the neighbors, is within bounds or outside of it. And the same for new column ID. So these could be like -1 and -1. Sorry, the deltas might be -1 and -1. But if the octopus that flashes is 0, this will actually turn them to be -1 and -1. So they won't fit between 0 and 9. I hope that makes sense.
Yeah, so even just one of the 2 coordinates is not inside the boundaries. It will be fails.
This is what this will generate, essentially. And then, sorry, I'll put this on a new line just to kind of clarify what they are. And then new row ID could be -1, for instance. And if it's -1, this contains will be false.
Exactly.
Or new column ID would have the same behavior. If this was -1, it wouldn't be within the boundaries, which are 0 to 9. Hopefully this makes sense.
One comment I have there is that notation 0.n is actually a little bit smarter than actually materializing a list, because it creates just a range object, and that range object keeps in mind only the starting point and the ending point. And then when you tell it contains, is smart enough to figure out not to generate all the values, but just check if that value is inside the range.
Yep.
Also, let's point out that n is excluded.
Smaller than x, for instance, for contains, or value larger than y. And this was meant to be a double pipe. This is probably what the contains does.
Pretty much, yeah. I haven't checked the implementation, but I expect it's built that way because it doesn't materialize the grid. Well, the range of values for you.
It might be
including the left one and excluding the right one. If you want to include the right one, you have to use the equal notation.
Yeah.
Is ... equal, yes. That's also another.
But we don't want it because our n is 10 and we want just 0 to 9 included or 10 excluded.
Yeah. So cool. All right. So that was that for how the boundaries check works. Yeah, I agree. It's not the most straightforward to read. Like this whole bit is a bit potentially confusing because it's a lot of code.
We can look at simplifying this if we have extra time in this episode.
Yeah, we'll do. So let me just undo all the changes because I want to keep this running as it was.
In Python, I solved all of this with a try except.
Yeah. Yep. So next, we're implementing an all-flashed function. What? What?
This might be needed for part 2.
It might be part 2, okay. Yeah, let's see what this thing does.
Because that function is basically checking, returns true or false if all the octopus flashed at the same time.
Okay, fair enough. I get it. I can see it's used in part 2, but part 1 just parses the input and then wraps. And then we're iterating 100 times and then summing the results. Cool.
So that line 113 deserves a little bit more.
I was going to say, this take works on iterators, and this basically means take the first 100 iterations over this and then sum. Because grid is already an iterator. That's what parsing returns. It returns an octogrid.
Take is giving back you another iterator.
Which one?
Take.
Yeah, I think it returns an iterable. No.
I think take is lazy. I think it just says, I'm going to keep iterating until that value, but you need to call a terminating action to actually trigger that computation.
Okay.
And in this case, sum is a terminating action because it actually starts the iterator and it will take all the items and sum them together.
Yep. So,
and by the way, when I say all the items, this is also another thing that might be a little bit confusing. So because an iterator has that next function, that next function needs to return some value or none. When we say sum, it's basically taking all the values for that some value and accumulating them together. So here is not accumulating anything from the grid itself, but from the iterator that we got from the grid. So we are using that custom logic that counts how many octopus have flashed for every iteration, and that number is the one that we are accumulating there for 100 times.
What I find very interesting is that we can do the take of 100, and there's no need to unwrap it in case it might be not okay because it returns sum. So you shouldn't be able to sum up a bunch of values and then a bunch of nuns.
Yeah, I think that we might need to check the documentation there, but my guess is that, for instance, if we were finishing the iteration before 100 cycles, right? Let's say that at cycle 20, we return none. So we generated basically 19 values. I think that's what you would get. So I expect that this is maximum up to 100, but it could be less.
I'd say yields the element until n elements are yielded or end of the iterator is reached.
Yeah.
So if it is 20 and the end is reached at 20, it will stop there. It will yield the 20 elements too, and then you sum the 20 elements.
Okay, so that's essentially...
Yeah, whatever comes first.
Yeah, so it iterates for as long as it can up to your maximum value, and then it expects you to do something with those values. And that's pretty much it. Okay, cool. So that's it for part 1, I suppose.
Awesome. Should we ever look at part 2?
Yeah.
Do we want to do the while sum?
Actually, let's run the test. And then
let's run the test. We can change the while to while sum and run the test.
So let me go to year 2021, exercise 11, cargo test first. Do you want to bench it just to see how quick it is?
I don't expect it will make a massive difference just changing the while sum, but we can try.
Remember that on our laptops there is a lot of noise when we bench.
Mine's probably got a bunch because it's running a ton of random stuff. Apologies. I can't turn off some of it, but not all of it. Like the stream, for instance, has to keep up.
Yeah, the Bitcoin mining also.
Yeah, 100%. No, man, this is my laptop. And my electricity. Cool. So we said we wanted to change this essentially, right? So while I'll just go below. So while sum.
So this is while let.
Oh yeah.
And then you can say sum x, where x is gonna be, for instance, the tuple row and column. Now leave just x for now, and outside the parentheses say equal.
Sorry. Jesus fuck, I'm an idiot. Sorry.
Where are you?
I'm Scooby-Doo. Yeah.
Okay. There you can say will flash.pop on the right hand side. Now remove all that row column. I'll explain this better in a second.
I'm really not sure what you want to do. Okay.
Remove the parentheses as well.
Yep.
Just say will
flash,
underscore flash dot pop.
Yeah, not pops, but pop. Okay.
And you have a double closing parenthesis there.
Of course I do, because I'm not good at typing.
Can you destructure the tuple in the sum? Or you have
so
to do that?
I just wanted to show that it's telling you that x is u sides, because what you are getting there is the tuple with row and column. But you can do the same thing even inside the x. So if you just replace x with a tuple saying row ID, column ID, that will also do the destructuring for you.
Perfect.
And now you can comment 64 and 65.
Oh yeah, because this has not been comment.
Okay, I like your comments.
We've got git. Git and undo. Okay, cargo test. Let's see if it's still running, right?
Okay, let me meanwhile explain better what this means. So this is basically doing this line 64 that we change. It's gonna try to do will flash.pop. If that that can return either none or a value. But what we are doing is that it doesn't matter what it returns. In order to do the while, to apply the while, we try to match the pattern. So what we are defining on the left side of this expression is a pattern. And this pattern is saying, I want to match a sum, and that sum needs to contain a tuple, and that tuple has 2 elements of u sides.
Yep.
And what it's doing, it takes the result of pop, and it checks if it's actually matching this pattern. And by the way, while it's doing that, it also applies the values that it's finding to all the variables that we have in our patterns. So it's also populating row ID and column ID. So it's also in a way doing the destructuring for us. So this is, of course, a lot more expressive, and it's allowing us to save that additional line. Like before, we were kind of doing while true. If it's not finished, then take the value. And because we are sure there is a value, and destructure the value. Here we are doing all this thing in one single expression.
Yep. We're essentially saying, while this thing can pop, get the values from it, and do these things.
Exactly.
In short.
And yes, I agree that the only good comments are deleted comments.
Oh, come on, pull comments. They are useful sometimes.
They sometimes have their value. Okay, I'm gonna commit this. Let's see if I have any other changes, because I did mess around with stuff. No, that's it. Okay. Change, simplify. While.
Meanwhile, I'll do a little bit of propaganda. If you like what you're seeing today, we just started recently to compare Rust with other languages. If you like doing that as another way to explore Rust, give us a follow so you can know the next time we are live.
So we only have a few minutes left for today, right? We could either take a look at part 2, or we could try to run some benchmarks.
I would say let's look at part 2. Shouldn't be too complicated.
Yeah, I think it's not very long.
So should I continue with Rust part 2, and then Roberto can do Python part 2? Or do you want to keep the original?
We can go to Python part 2, but we can read the README before.
Actually, that's probably the best place to start.
So let me switch the screen, because I think if I do it, we'll get a little bit of a better preview.
Yeah, you're right.
And I think at that point, we can go fairly quick. All right, so in part 2, what we want to do is that, well, this is still giving us more stuff. But basically, what they want to show us is that there could be a case every once in a while where all the octopuses are flashing together, right? So basically, what we want to know is what is going to be the first time where this particular configuration is going to happen, which basically means every time we are doing a loop and generating a new iteration of our simulation, if we see that every single octopus has flashed, then we know we should stop and return the number of iterations. This is literally what part 2 is asking us. Make sense?
It does.
So it shouldn't be too complicated based on the utilities we have built already, but we need to implement this additional check and decide. We don't care anymore about how many are flashing in total. We just need to count the iteration and return that number of iteration when we reach this particular configuration.
Well, the count of flashed, sorry, just me thinking, could be very useful, because we know how many octopuses we have in total. And the iterator tells you how many flashed, so you can just go until the numbers are equal. And
that's true. That's true. Maybe there is
count, right?
There is an optimization that I didn't realize.
You mean if all of them flash together, they will be at 0 the next round?
Yeah, in your case, because you're returning the grid, yes, it'll be a grid of zeros. But in the Rust example, you return the number of flashes. It's literally that. So if the number of flashes equals 10 by 10, or however big our grid was, that's it. They all flash. That's the number of iterations.
Yeah, we don't need to check all the single cells to see if they are 0. We can just see if the total flash for that round is 100, basically.
We can try that later, and we can actually even do a benchmark for that, because it'd be interesting.
Cool. Okay, I'll put back Roberto's screen.
Yeah.
So, can you see the screen?
Yes.
Okay. Here, part 2. Basically, is a copy and paste of part 1, because laziness, not declaring a function. But I could have recycled the function from the step before, but I prefer to copy and paste, because the function is exactly the same. Didn't change at all. Here, what I changed is just that now I'm counting. So, for my j in my count by 1, My grid, I don't care about how many flashed. I did the same approach as Luciano. So I'm just checking if all of them are 0. I step over my grid until all cells are 0 for all the Y in the grid, for all the cells in the row. If they are all 0, I break.
Mm-hmm.
After the for loop, J will still be initialized, and it will be the number of the step that triggered the flatness of our.
By the way, that count function, sorry, Robert, I've never seen that one before. Does it just create an iterator that continues forever?
Yeah, this one
and
is
it
just
will increase by 1 every time, right?
By what you tell. Yeah,
Okay.
It can start also not to 0, but from something else. By default, starts from 0 and goes by step, and it goes forever. This one is just a generator that goes on until the end of the world. And for this reason, I have to break in our ending condition. And if we go to the graph, this graph at this point is, in my case, 320 steps. And like we saw before, the numbers are rising. Then if you see the flat part that is on the front of it started to become larger and larger, because with these rules, the flatness is converging, basically. So let me skip almost to the end, otherwise we stay here more. So you see that it's becoming flatter and flatter at every loop. And at one point, they will all synchronize. Yeah, then they're starting again. Let's go to the very end. At the very end, we have... Stop. Thank you. The very end is this one. We have everything flat. The step before is this one, where some of them are very near to flash, and then they will flash together.
Will they? I'm curious now. Will they flash out of sync after flashing together? No. Presumably they're just...
No, because here they just go on forever at the same...
Yeah, they'll be together forever, basically.
Yeah, they will just this flat plane, this flat... they will flash at the same moment and charge at the same... speed.
Cool. Okay, so let's go through or unless there are any questions about the Python version, we can look at the Rust solution that we have, and then we can look at just checking counts and see if that's actually any better.
Yes, so let me switch desk.
Julio, let me know when you've switched to my screen.
Should I be coming up right now.
Yeah, there you go. Cool. So what we have here, actually, let's look at the part 2 code, which is basically same as the first one, parsing the input. It's keeping a track of however rounds it took, and we're initializing this to 0 usize, which is, I assume, a shorthand for the value of 0 as a usize. And while the grid all flashed function is false, we keep iterating and increasing the number of rounds it took. What all flashed does is it returns the true or false. It goes through each row and each cell, and if either of them is not equal to 0, it returns false. Remember, we reset them to 0 once they all flashed. So this is one way of doing it, which is, let me run I'll need to go to the...
cargo bench,
Yeah. Jesus, I can't type. I'm sorry.
I think if you click on the right side in the previous terminal, you might be already there. You see on the right side, you have a list of terminals.
This thing. Jesus, are these all running?
Probably.
Fuck. Sorry. Yes,
I think there you are already there. Okay.
As you can tell, I don't use VS Code very much, or very well anyway. Okay, cool. So let's run a cargo bench. This will take a little while.
We can do in VI if you want next time.
I don't think the viewers will appreciate me using Vim. I don't know. I do use Vim most of the time, but yeah, we'll see.
I think if you are able to use it, I'm not, so.
I don't want to expose anybody to Vim unnecessarily. Just use normal text editors and don't use this one.
Okay.
Don't try this at home.
Yeah, exactly. Save your
sanity. We will have to raid some Vim expert today at the end of this stream.
Sure, fair enough. Okay, so then I suppose what I was proposing for part 2, if I can find it again, we're not going to save while this is running, is instead of this, we can keep the rounds thing, and then we can just go while grid next not equal to, how many are these supposed to be? 10 by 10, so 100?
We might have to change the syntax, but okay.
Yeah, you get what I mean, right? This, basically.
Yep, that might be a solution.
But let's let this finish before I save. Does it not know how to do this?
Because remember that exactly. So you can use the while let again.
Yeah.
Or do the unwrap thing.
Let some
of 100 literally.
Yeah.
Yeah, it takes a bit to get used to this matching syntax, because you can use both values and variables, and it will apply the variables for you.
But wait, sum of 100 will expect this value to be, so it will be
100.
false. Yeah, it will be false.
But you need to give it different, actually.
I can't give it not equal to.
You cannot give it not equal, right? So maybe in this case you cannot use pattern match.
No, or maybe we don't know. Let's try it with unwrap first. Okay, so this thing ran them. Part 2 was 1.1 milliseconds. Keep in mind there will be a ton of noise from my machine. There you go, I commented it wonderfully. Rounds, okay.
You need a semicolon.
I was unsure if I do, because I'm not returning it, so yeah. Okay, and let's run the benchmark again and see what happens. Yep, all flashed is not used. Yeah, okay.
That shouldn't affect the benchmark.
What? Sorry, I just started it. Sorry. I saw these not found. I was like, crap. Is it broken? No. Yeah, so let's see if it's any faster than 1.1 milliseconds.
Meanwhile, there is a joke going on here in the chat with sorry Roberto, but I think I'm missing what's going on.
About the comments, probably? No idea.
Oh, okay. Maybe it was about the fact that you say that there are good use cases for comments.
Yeah, there are good comments, not only bad
ones. Fair enough.
Fair. Okay, so there's no real difference. It's like, it's also 1.1. It's like... Well,
5% is not...
It can still be...
If I run it again, noise. It might just be noise.
Because I mean, at the end of the day, checking 100 numbers is not a lot, I guess. Yeah. But we are doing that multiple times in a loop. Yeah. So all over there might be a little bit of an improvement.
To be honest, what I like more about this is that we're not checking each and every value unnecessarily. Like look, this time it was actually quicker. It was actually slower, sorry, than last time. But instead of going through each of these, which is kind of a lot of code to digest, we're looking at a value that we're already returning, which is how many flashed. Again, I think this is a simpler solution.
I think so. Yeah, this is a case where I will add a comment, where I will say...
Yeah, to explain why.
If we see that 100... Actually, this is interesting, because here we know that the size is 10, right?
Have you run the test to see if the answer is still good?
Oh, yeah, you're absolutely right. Let me do that. I ran the benchmark, which should run the test, right? No, it's not running the test. Yeah, they're still passing.
I don't think the benchmark are asserting anything.
No, they just run the function multiple
Part 2, okay. Yeah, but it did still pass, so it works with this approach. Okay, so do I leave both of them in?
I would remove it and just add a comment like, we check 100 because we know there are 100 cells. So if all flashed is 100, that basically means that they all flashed.
Because we have a 10 by 10 grid of 100
octopus
pi, because that's the correct plural apparently.
Oh yeah, it's Latin.
All right. So we check against 100 because we have a 10 by 10 grid of 100 octopi. And our grid returns how many flashed.
And they can only flash once per octopus per round.
Yep. And our grid returns how many flashed, and can only each octopus sorry, can only flash once per round. Jesus, this is
you can split it in 2 lines.
Yep. Our grid returns how many octopi flashed, and each octopus...
Yeah, that's
probably better. Each octopus can only flash once per round, and our grid returns how many octopi flashed. It should be clear enough. Do I leave this in, or
I would remove it and also remove the function, because I mean, there isn't much value in this function.
just to compare, even in Python, comparing the number with 100 on doing the if all is not changing the performances. And just to give a number, Python is taking 40 milliseconds instead of 1.1 milliseconds. So Python is 40 times lower.
Okay. Yeah, that's quite a lot. Quite a lot.
But
now,
Rust is compiled, Python is interpreted.
There's also a difference between machines, presumably, and how busy they are.
Yeah, the machines are not the same. I'm running that remotely. Yeah, okay. But
if
even
we want to
in
do a
case,
fair comparison, we can do it on like a very controlled machine that runs just the Rust thing or just the Python thing. And even then, you get differences between different machines. So
and we can use again the Raspberry Pi Pico because it can run MicroPython.
Yeah.
Oh, nice. Yeah, that's a good way of comparing. But MicroPython is compiled, right?
MicroPython is still in an interpreter. So the Python itself is compiled, obviously, is a C executable, but the code is interpreted.
Also, it will give you like a compiled binary with the interpreter and your code.
Then
right?
your code is not in the compiled binary. Your code in Raspberry Pi Pico is in the QSPI flash memory. So it's an external flash memory. You can edit it on the fly, connecting the Raspberry Pi Pico with USB cable to a machine. So it's way easier to develop.
Right.
It's just a USB drive with a Python file in it, and then you can run it. But obviously, being interpreted will be slower. Probably not 40 times like now, obviously, because my machine, your machine, different machines. I'm not running that on my machine, to be honest. I'm running that in the Google Drive once. So who knows what is there, what is a core for them.
True. So I'm gonna commit this and push it. And do we leave it here, or do you think there's anything else interesting that we could go through? Also, if anybody in the chat has any other interesting questions about any of this. Also, thank you so much for all the comments and questions this time, because they were like super cool.
Yeah, I agree. So I'll probably leave it at this for today. So I'll move to the other screen.
So we can wrap it up. You can find the recording on YouTube. The link is on the Twitch on Twitch in the About section. If you're watching this on YouTube, we do live streaming on Twitch every Monday, 5 p.m. UTC, 6 p.m. Dublin time. Make sure to check the Twitch link in the YouTube description. Give us follow, subscribe, everything. Feel free to leave comment on our PRs. The repository of the code is on GitHub.
And I will put the link at some point, but if not, you can find it also linked in the bio on Twitch.
I'm going on. Everything is well accepted. We're trying to learn Rust, so don't expect our solution to be the cleanest and more idiomatic ones. Like, for example, the while we fixed it online, live, because we learned that last time, probably. We did that last time, and we improve our solution while we go through. If you know better ways to solve the problem, let us know. Thank you for all the collaboration in the chat and the questions. Luciano, do we write somebody, or we are not able to do that?
That's what I'm looking for.
With the new setup, can we write people?
Yes, we can. So we'll see you next time.
See you all.
Bye.